phase system. We say two component system. So we call it a mixture, right? Possibly if you have a liquid solid mixture, maybe there may be 3 liquid, solid and gas. So likewise there we have mixtures. So first we can discuss about the binary system. Binary means we have only 2 components, right? So in that mixture we have only 2 components. It may be liquids, solids or gases. So in the vapors, right, we have a pressure, as you know, but in liquid we do not have some kind of a pressure, and again solids we do not have a pressure. But if you have vapors, then we can discuss about the vapor pressure. And again, if you have a liquid system, we know that due to some vaporization effect, there may be a phase of vapor, that means a gas is touching with the liquid phase, right? So in a cup of water, we can't see that, but if we can do some kind of testing, we can identify there is a water vapor is touching with the liquid phase, liquid water, right? That is also a system. So in that case, we have to measure the pressure of the vapor which is touching with the liquid. And again, the composition of the solution. As what we say, if we solute some of the materials like salt inside water, so we add some amount of salt into some amount of liquid, as like if we get 100 grams of salt, so we solidify that in a 1 liter of water, then there are maybe some kind of amount of salt, amount of liquid there. So we have to identify what is the fraction of water or what is the fraction of salt. We call it a fraction, right? So that fraction we can identify the amount of the component that we consider, as example salt. So if we just get those things as 1 unit, is like if we can identify the grams of water inside the grams of salt, and if we identify the moles, the amount of moles inside water and moles inside salt. So likewise we can discuss the fraction of solution, right? So these are the requirement to identify those mixtures, that means systems. It may be binary or tertiary. It depends on the component that we add. Then again, ideal solutions, right? So what is called ideal solution? It's a mixture of solids of similar chemical structures. That means all of these components have the similar chemical structure. It's something like liquids or solids, right? Very same. Then linear relationship of boiling point and the composition. So those are the things we need to identify under a mixture, right? So here you can see a diagram, binary system, right? Here we have one component and the other axis is another component. So if we increase, here you have a hexane and heptane mixture, right? In this right hand axis you can see 100 hexane. That means in that area you have 0 heptane and 100 hexane. I think you are very familiar with this kind of graphs. So in this left hand axis you have 100 heptane, 0 hexane. So in between that you can see some amount of hexane is possible, and again some amount of heptane is possible. We call fraction, right? So that fraction is the most important part of a phase diagram, right? So after this discussion we are trying to identify these fractions inside those mixtures, right? As example, if we mix, here you can see this axis is nominated as the boiling point, right? Boiling point. So you can identify if 100 heptane is there, then the boiling point of 100 heptane is 98 degrees Celsius. But if you have 100 hexane, it's going to be reduced into 69. So if you have a mixture of hexane and heptane, so the boiling point should be in between 98 and 69. Right? This is a binary phase diagram. That means a very simple phase diagram. As example, if you have 20% hexane and remaining 80 is heptane. So if you identify the fraction, if you identify in between these two, right? As example, a point like this, right? Here you can see the amount of hexane is less and the amount of heptane is higher, right? As example, if we say here 20% of 20% hexane and the remaining 80 is heptane, right? So like that we can find out what type of fraction is there. So if we select this type of one, so that mixture is different from 100% hexane or 100% heptane. So that means that mixture is not as equalized with the boiling point of 100% hexane or 100% heptane. That means the boiling point of that mixture is different from both two. So in that case, we have to find out what is the boiling point of that mixture, right? So if you have a diagram like this, if you draw a line like that, then the point where these intersect, you can find what is the exact boiling point of the mixture. So likewise, we have to deal with those phase diagrams. That is the most primary phase diagram that I use to describe what is called phase diagram. So we discuss what is non-ideal solutions. So non-ideal means mixture of liquids having dissimilar structures. It means have marked deviation from the linear boiling point composition relation. That means we can't just identify what type of mixture in that components. That is called non-ideal solutions. Identify the fraction. We have a law that also already you have learned in your advanced level. It is called Raoult's law. I think most of you have used this one in your chemistry paper, right? But here I know that there are some guys who are with commerce background, so I try to introduce this Raoult's law for you. This Raoult's law describe the amount of component inside the solution, but that is a vapor pressure, right? If you have vapor components, then you can add this Raoult's law. So if you just mix two components A and B, right? So the partial pressure of A we call PA, then partial pressure of B called PB, right? In the Raoult's law, they said if you want to find the partial pressure of A, so you have to multiply the moles fraction of A into that means POA pressure. Right? If you have POA in that that means container, so you have to multiply that one by the mole fraction of A to find out the partial pressure of A. As like if you want to find partial pressure of B, likewise you have to multiply by the mole fraction and the vapor pressure of POB, right? That is the Raoult's law, right? So total pressure of the mixture, you can find Pt equals Pa plus Pb. Then you can apply this to here, Xa Pa naught plus Xb Pb naught, right? So to identify a small example here, right, I have added 3 examples. So I'll give you 1 minute to find by using this equation. Right here you have equation Pa equals Xa Pa naught, Pb equals Xb Pb naught. So first example you have Na, that means amount of moles of A, 0.2. So please try to do this one now to have some experience about the equation, right? I think most of you have experience with that, but some of you guys do not have some amount of experience. So please try to do this one now. You have moles A 0.2 and moles B is 0.5. Then total pressure is given 40. So this is the POA pressure is 20. We have to find POB pressure. Right. So please get a small sketch on this one and try to figure out the equation and use these values and find what is PB naught. Right. Na is 0.2, NB is 0.5. By using this one here, right, you can find PA. Right, we have the PA and PT is there. So PT means XA PA naught, XB PB naught. You can apply this equation directly. So if you want to find XA, this is XA. Na divided by Na plus NB. Right? Here Na plus NB is 0.7. Na is 0.2. Then XA, right here, XA is 0.2 divided by 0.2 plus 0.5, that is 0.286. Then XB is 0.5 divided by 0.2 plus 0.5, that is 0.714. That is XA plus XB, totally is 1. Then if you add that one into the PT, then PT equals XA PA naught plus XB PB naught. Then PT is 40. Then XA is 0.286 into 20 plus XB is 0.714 into PB naught, right? Then it seems PB is 48. So this is about Raoult's law. So again you have second one, right? P methanol is 90, P ethanol is 45. What is PT? Right? Simply you need to add those two. But again, here another third one is there, P naught P, P naught Q is there. I need to find PT like. Right? So these are some simple examples, right, to practice your Raoult's equation, right? So you can practice it. Yes, any questions regarding that Raoult's law? If it mixture of solids that obey Raoult's law are known as ideal solutions, right? So ideal solutions, you have particles of A, then particles of B, then after mixing you have a liquid mixture of A and B. So in that case, we say that is an ideal solution if the strength of intermolecular interaction in POA is closely equal to the strength of intermolecular interaction in POB. This is closely equal to strength of intermolecular interaction between particle A and particle B in mixture, total mixture. So if you have the total bonding strengths are equal, right, comparatively A, B and the mixture, right, if the total are equal, then we call it an ideal solution. So the escape tendency of molecule A or B in mixture equals to their respective escape tendency in POA and POB. That means they have the equal chance to escape by mixing all of this A and B is same as the PO that particular material. No enthalpy change, no volume change upon mixing. So reason interaction doesn't change upon mixing. So more nearly alike this two substances are chemically, the more nearly they exhibit ideal behavior, right? That is why we say that is the ideal solution. So here, which of the following solution mixtures are ideal solutions, right? So as example, benzene and methyl benzene are ideal. Cyclohexane and ethanol is not ideal. So likewise, you can identify those mixtures ideal or not. But if you want to do these kind of calculations, you have to select ideal solutions, right? So this is the vapor pressure composition curve, right? So vapor pressure means, so in the previous also you identify here, this is the that means XA, right? So this is the 100% of XA, and this is the 100% of XB and 100% of XA. Right, here you have POA and here you have POB. Right, this is the diagram, right? So in between A and B, so your mixture is in between PA and PB. Right, P not A and P not B, in between these two you have your mixture, right? That is your mixture. So in that point we have vapor pressure in the y-axis, right? So in a given mixture, so you need to find out what is the total vapor pressure of the mixture, right? As example, here you have 0.6 XA and 0.4 XB, because total should be 1 if you have a binary system, right? So if you want to find out what is the total pressure in these fractions, means if you mix 0.6 XA and 0.4 XB, then what is the fraction of, what is the vapor pressure of this one? Then if you have a diagram like this, then just you need to draw a line vertically and find out what is the amount. That is the advantage of having phase diagram, right? For ideal solution, PA is going with along with XA and PB is going along with XP, then PT is PA plus PB, right? So if you want to find a pressure in between these two, easily you can find PA plus PB. Then boiling point also, this is again one of a phase diagram. So in the previous case you have vapor pressure, this point you have the boiling point as what I explained. So this is a kind of a phase diagram, binary phase diagram, a very simple one. That is why I explain these things, because at the end you need to identify one of the complex phase diagrams when you are using in your industrial applications. So to going into that before, you have to identify the simple ones, right? Again here also you have XA and XB, so you can identify the boiling point in between these 2 points. That is the advantage of having this kind of phase diagram. So here this is a liquid contain 1 mole of A, 1 mole of B, P naught is 10, PB is 30, right? So this is a composition, right? XA is 0.5 and XB is 0.5. So partial pressure, you can see if you multiply this one by 5, you have again B total here. So likewise, you can do those calculations if you know the fractions. So those are ideals. It is called Raoult's law. So for non-ideal solutions, this solution is some called deviations. It shows some deviations if you have non-ideal solutions. So only if you want to use Raoult's law, you have to find out whether this solution is ideal. If it is ideal, then Raoult's law is applicable. But if there are deviations from Raoult's law, you need to find another way. So how about those makers do not obey Raoult's law? It may be solution with positive deviation and again negative deviations. That means you have positive deviation from Raoult's law and again negative deviations from Raoult's law. So here positive deviations, right? It seems strength of intermolecular attraction POA plus strength of internal POB is higher than the mixture bonding. That means A and B, right? So they are mixture. That strength of intermolecular attraction is lower than A and B. So it seems it is called positive deviation. Positive means your A and B is higher than the mixture, right? So if you have a positive mixture, so the vapor pressure would be higher and the boiling point would be lower compared to ideal behavior. So if you have positive one from the Raoult's law, then your vapor pressure is higher than your ideal one and boiling is lower than the ideal one, that it says, right? As example, cyclohexane and ethanol. If you have a mixture of cyclohexane and ethanol, it seems it shows positive behavior from then negative deviation. So negative means strength of intermolecular A, strength of intermolecular B. That means if you mix A and B, then you get a mixture of AB. So that strength of intermolecular is higher than A and B, right? Your POA and POB is your strength is lower than the mixture. Then it is called negative deviation. So if you have negative deviation, the vapor pressure would be lower, right? So that curve, this is the original curve, it is ideal. Then negative one is lower than that. And the boiling is higher. Because your mixture strength is high, then you need more energy to get vaporized, right? That is why this boiling point is higher. So those things are coming under very test. If you do so many tests and identify this type of, because you need to mix 0.2 and 0.8 and again you need to give energy, that means you need to heat up. Then after heating you can find up to that level which degree of Celsius is getting, total one is boiling, right? So that point you need to identify using some of the tests. So after doing some test, given positives from the Raoult's law. As example, ethanoate and the trichloromethanate, right? Those are some of the examples for negative behavior from the Raoult's law, right? So these are some examples. So I need to explain all of this because that is not the main thing you need to describe, but I have to do these primary things before going into our major one. Right. Again, this is one of a phase diagram curve. This is the vapor curve and this is the liquid curve. In between you have liquid plus vapor. Right. So you can identify how it change. Right. This is negative and this is positive and this is negative. Likewise, you can identify. Right. So in a phase diagram like negative and positive from the Raoult's law, here you can see fractional distillation, right? Fractional distillation, I think all of you heard about this crude oil distillation, right? So if you in the Sabukastanda, you know, in early years they have refined those petrol, diesel and gasoline, all of that from the crude oil, right? That is called distillation. So if you have a mixture of all, here what we are discussing only two, right? So in that case you have a mixture boiling point and pure boiling points, right? So this is kind of a mixture of A and B, right? Here you can see the boiling point. So if you have a mixture of A and B, then if you get a crude oil as example, right? If you have A and B mixture of crude oil, not the other. So consider like that. So in the crude oil, you can identify what is the fraction of A and B. We call mole fraction, right? So if you consider A, that X in the X point, you have less A and higher B, right? In this X here. So in this point, you can identify what is the boiling point of this mixture, right? Because you have only liquids now, right? So if you just energize, that means if you heat up the mixture, then it goes more than your liquid and goes to vapor. So that is what we call uh, vaporization or boiling, right? So if you have a mixture, right, here you can see the room temperature. Then if you heat up more than the room temperature, if it is goes to point where Tx, right? So if it goes to Tx, because you have liquid phase, right, this is the vapor phase. So after liquid phase, you have a mixture of, so in this area, that means in between these two curves, you have liquid and vapor. So now in the, if you have your room temperature like this, so this is your room temperature, it is we call 30, right? So now your mixture in the room temperature. So in that mixture you have two liquids now. So if you try to heat this one up to T1, right, as like we say 70, right? So if you try to heat up your extraction into this one, so up to this point, that means you have liquid. But after that, it try to goes to because this is the same temperature, right? So same temperature, it goes to this point. This is the vapor pressure of this amount, right? Because some amount of vapor is getting removed and it will change up to some, right? So then if you just cool down this position here, that means it goes to vapor here and then you just cool it, then that position becomes here third. Now it has changed your composition because some amount of vapor is removed. It's due to the boiling point. Now your fraction is getting changed, right? Again, if you heat up that, then it goes to Ty, that is the boiling point of that mixture. Now that is changed because here we get some amount of X and Y, right? So this is the kind of a distillation system, like you know that, right? I don't want to explain. Then this is called fractional distillation, right? You have liquid and phase. This is a petroleum refining, right? First you get gas oil and then kerosene, naphtha, petrol. Likewise, after the total goes, right, total gases comes out, and at the lower level you get bitumen or tar, right? Lubricants. Likewise, it getting from the fractional distillation. So this is not a binary system. You have so many components there, but we are discussing only about the binary system. So in the binary system, you have we call azeotropic mixtures. So azeotropic means in between that also you have a kind of a point where these two are not existing, only one exists, right? So liquid mixtures is deviate negatively from Raoult's law, show a maximum in the boiling point composition curve, right? That means we call negatively deviate. So in the negative one, you can see that vapor pressure is high, then you have a in between point of M. So in that case, if you just comes from this side, and if it just comes from this side, that is different, right? You can see that. If you just go with this one, so remaining is here, right? Start from X, if you distill POB, right? If you just heat up from X, then it goes here, then move to this point and this point, and again you have POB. But you just start from this one W, right? It only remains this point. That means you can get A, right? So that is the difference. Then positive ones also you have like this. Positive one means if you just do it from X, start from X and distill in a zerotropic mixture M, you can have a POB because it moves to this point. So start from Y, if you just, it moves to this point and you can get POA, right? That is the difference from the negative and positive. So here I have included some of examples to go through, right? So that is called phase diagrams. So in those primary things you can identify. Now what we are trying to understand right now, we are trying to move into that. So any questions? Describe what is a phase. It is a region in a material that differs in structure and function from other regions. Now you know that. Then phase diagram represents phase present in metal or any metal, liquid, spheres, likewise different conditions with the temperature, pressure and composition. Now you have some familiarity with that also. It indicates equilibrium solid solubility and of element and another, and indicates the temperature range. You can identify up to what level that it seems. Then pure substance exists, solid, liquid and vapor. Total one is that this is a kind of a phase diagram. If someone is having some experience with that, you also know it, right? Then different phases coexist at triple point, right? Triple point means three phases are equal, but in the previous cases you can see we have only binary system. That means we have liquid, vapor, or solid, liquid likewise. But in triple point you can identify solid, gas, liquid. All of three are at the same point, right? That means you have that point where the solids, liquids, gases are exist in the mixture. It is called triple point, right? So here you can identify some of complex kind of diagrams, complex phase diagrams. So from the point now we have to identify this kind of phase diagrams, right? So this is under your industrial applications. So to identify this one, here also as like Raoult's law, you have a rule called Gibbs phase rule, right? So in the Gibbs phase rule, you have a number of phases that coexist in system, right? That is P. The number of components, C, and the degree of freedom. So degree of freedom means how much you can deviate from the linear, that means ideal system. It is called degree of freedom. So number of phases plus degree of freedom is equal to number of components plus 2. That is called Gibbs phase rule. Right? For pure water at triple point you have three phases. There is one component, water. Then degree of freedom is 0. Only the water exists. So therefore 3 plus F is 1 plus 2. Then F it becomes 0. So degree of freedom indicates number of variables that can be changed without changing number of phases. Right? That is the degree of freedom that indicates how much that you can work out with the mixture. Right? So here also cooling curves. I think all of you have experience in your ordinary level what is cooling curve means. Right, in the cooling curve you can identify if you have a kind of mixture with higher temperature. If you go down with the cooling rate, then how it change. So cooling curves used to determine the phase transition temperature. Phase transition means, as example, if you have it means 60 degrees Celsius water, right? If you heat up to 60 degrees Celsius, it still remains liquid. But if you try to cool it down to 0, then what happens? Your liquid is getting changed to solid. Right? That is the changing temperature we call phase transition. It comes to liquid phase to solid phase. It is called phase transition. So that is the advantage of having a cooling curves. Right here you can see so many PO metal, and you have iron here also. So temperature and time data cooling molten metal is that, and the temperature and the time. Right here you can see this is the pouring temperature at A. So if you reduce the temperature, that means if you cool it, then becomes to B, and you have a kind of session. That means if you have kind of a time period that there is no temperature difference, right? At the point you know that those transition periods, that means if you change solid into liquid, so in that temperature there is no, we call it melting. That melting temperature, you do not have any temperature change, but time is taken to break those bonds in the solid to become liquid, right? So after that, again, if you increase the temperature, then liquid becomes vapor. As example, I said if you have ice, right? Then ice means 0 degrees Celsius. It becomes solid. Then if you melt it, then as the same temperature, that means 0 degrees Celsius, it becomes liquid, right? So same degree. Same means in the solid phase you have again 0 degree, and again liquid phase also you have 0 degree. But you need to heat up. It means you have to provide heat. So time is consuming, timing is passing, right? So but same temperature, and only the phase transition happen, right? So likewise you can identify some of the things from the cooling curves as well. So thermal arrest means that heat lost equal heat supplied by the solidifying metal. So at the phase transition, so likewise these things happen again. And develop a phase diagram using cooling curve, right? So here also a series of cooling curves are different metal composition first constructed. So you have different composition, that means molecular composition. Then point of change of slope of cooling curves, thermal arrays are noted and phase diagram is constructed. Likewise here you can see there are different type of compositions. Here pure copper, right? If you have pure copper, then 1400 degrees Celsius. If you cool it down to again here 109, 110 like temperature, that phase transition happen. Here you have liquid, so after that you get solid, right? That is called, here you can see that is the melting temperature. So using that, here you can see 1084, that is the pure copper melting point. So in that case you can draw it here and see what is the melting point of copper. As like this is a combination of copper and nickel, right? So after some there are, you can see 20% nickel, 50% nickel, 80% and pure nickel. Likewise you can change the composition and find out what are the kind of transition temperatures. So if we have L1 here, you can plot it here also, and this one you can plot it. So likewise you can construct this one. And that is how we can use our cooling curves to develop phase diagram. Now you can see this is a phase diagram, right? This is the liquid, and now it solidify, it is solid, right? This is the solid phase and this is the liquid phase. Now you have a liquid solid 2 component binary system. This is your cooling curve and this is your phase diagram. So at that point here, because this is a parallel to X, if you have a melting point, it is parallel to that one, because that means your liquid phase and solid phase are coincide. So in that point, that is the we call melting point. As pure nickel here also, C and D, you have parallel to X axis, So that is also coincide with C and D. It becomes the pionical melting point. So using your cooling curve, that means if you change some of your chemical composition and do this kind of test, and you can construct this phase diagram. This is a binary phase diagram. Right now I think you can identify this is one of a primary phase diagram, and here you have solid phase and liquid phase. This is a solid and liquid phase system, right? So in that phase diagrams, you can apply the lever rule also. The lever rule gives the weight percentage of phases in any two phase diagrams. So lever rule you can use to find if you have unknown phase. As example, if you know what are the composition about WT and WS, these 2 points. If you want to find out W naught, this is the way to find the amount here, right? You have to get the weight fraction of solid phase, right? Then W naught, you know this one, right? The fraction W naught minus W1, this amount. You can divide that one by WS minus WT, right? So that also equal to W1, right? WS and WL, solid and liquid. WS here, this one and this one, right? These two, you know, this is the name also change lever rule, but you know how to calculate this fraction also, no? Then XLS you can calculate, right? That is called lever rule, right? So if you want to find out, you can use it inside your phase diagrams, right? Now I think you have some idea about a phase diagram. So after that we are developing our phase diagram. Then there are some kind of systems to identify inside a phase diagram, because here we are discussing only the binary system. So within that binary system, there are some changes happen. As example, if you try to add some different things, right? So inside that system also there may be some different solidities developing, right? As like if you just add, you know, that sodium plus to chlorine minus, you know that difference, right? If you just add sodium chlorine, there is a sodium chloride middle crystal, right? It differs from sodium and chlorine, right? So in between that also you are developing some kind of a change. So we have to identify that that kind of changes also. Then we have some systems in between those phase diagrams, right? Then common types of phase diagrams, we call it types. The different metals can combine in different ways in solids as well as in liquids. Then depending upon the solubility characteristics of two metals, binary phase diagrams, they combine and they form this side of systems. First one is called isomorphous system. In the isomorphous system, two components are completely soluble in each other in both liquid and solid states and exist in a single phase for all composition of the alloy, right? So that is wordings, how we define isomorphous system. Okay, we'll describe that by using our diagrams. First, we try to identify. Here one system is there. It is called isomorphous. Then you have eutectic system, right? Eutectic means two components are completely soluble in liquid state, but either partially soluble or completely insoluble in the solid state. That is another system. This is due to that atomic structure and the bonding. And you have primary and secondary bonds. So due to the effect of primary and secondary bonding, these kind of systems may develop. Then peritectic system, It is the melting points of two metals differ considerably and liquid phase combined with solid phase to produce a new solid phase. Okay, we will see what it described from the diagrams also. This is the wordings that they have defined. Then monotectic system. In this system, one liquid transforms into another liquid and one solid. Right? Then Eutectoid. Again, phase diagram which transformation will take place in solid state. One solid composes into two different solids. Then Peritectoid, two solids transform into another solid. Right? So this is again how these kind of components are changed after the mixing. That is what we call a system. So we have to identify in our phase diagram is monotectic is there, or eutectoid, or peritectoid, right? So when you investigate or when you going through this kind of phase diagram, then again we have to identify this type of systems are there. Okay, we will see. This is a binary amorphous alloy system. Yes. So this is the binary we call isomorphous system, right? You have binary alloy, that means you have two components as like copper and nickel, right? So we mix it, then we mixture of two systems, then you have two component system. Now you know what is component and now you know what is system, right? So you have a mixture now. In the isomorphous system, two elements completely soluble in each other in liquid and solid state. That is what it says, isomorphous. Example, copper nickel, right? So here you do not have any changes. This is a pure line, right? From here you see copper 100, nickel 100, you have only pure line. This is the isomorphous. So in between these, there is no any changes of this line. That means there is no any solids are formed, right? Only copper and nickel, right? Right, solid solutions. This is the solid line and this is the liquid line. So in between there is no any forms, right? So if you get a point where like this one, a point like this, right? So it only has copper and nickel, it forms. So if you get the weight, you have 45 weight of nickel here. If you get the weight of here, you get 53 of nickel. Okay, that is only in the isomorphous systems, right? So composition at liquid and solid phases at any temperature can be determined drawing a tie line, right? So if you have isomorphous alloy system binary, so this is only binary, you have tertiary, likewise you have so many binary systems. So basically we are studying only up to your level for the binary system, right? So if you have a copper nickel solution in an isomorphous system means purely you can identify those lines, right? So like this one, if you purely have a solid and purely have the liquid and solid and the liquid system. So this is the that means you can easily differentiate both three. You have liquid separate, you have solid separate, and you have liquid solid mixture separate, right? Then binary eutectic, right? So if you just read this one here, this is the isomorphous. Two components are completely soluble in each other in both liquid solid state and exist in single phase for components of the alloy, right? Here you can see if you get this one only single one, this one only single one. That is the because in this line here, this line you have only the solids, in this line you have only the liquids, right? In binary eutectic alloy system, it says in some binary alloy system components have limited solid solubility, right? You do not have any type of changes, right? Here you can see this is the point, right? From here to here, in the previous case, we have single line. But what happens if you have a eutectic system? That means uh, limited solid solubility. That means they are not purely, that means totally soluble in between each other. So here it just goes from here to here, not a single line. It just drops somewhere, right? And it face something different from these two, right? In this point, right, you have another phase, right? It just not goes purely to here and here. So in that point, this is called eutectic, right? Example, lead tin alloy, this one, right? So this is, you can see this is kind of a complex phase diagram, right? So in that complex phase diagram, you can identify eutectic composition freezes at lower temperature than all other components, right? That is the difference, because here I'll see this is the pure tin melting point, and this is the pure lead. But in our previous cases, you can see, right, in that one, both are having in between these 2 points, no just below on this one, right? There is no below on this one, there is no higher on this one. But here you can see this is your lower level, but that position here you have lower melting point than these two. That is, it says eutectic composition faces lower temperature than all other composition, right? So that is what eutectic. So this lowest temperature is called eutectic temperature, right? So that is the difference of eutectic system. Both are binary, right? So liquid, then eutectic temperature cooling, it changes to another we call alpha solid solution plus beta solid solution, because in between these two also, but it changes to somewhat else, right? You have alpha and beta, right? That is alpha solid solution and beta solid solution. Those are names, right? Alpha and beta. So it says that in between lead and tin. That is the difference, right? Which is called binary eutectic. Here, this is the change, right? In between these two, you have another third system. In eutectic system, components A and B are completely soluble in liquid state, but completely insoluble, partially in each other in the solid state, right? Liquid you have here also, right? This is change due to some extent of the solubility, right? So liquid, definitely calling you have solid 1 to solid 2, and it changes, right? Liquid, if you cool, it changes to solid 1 and solid 2. But if you heat up, only one liquid. That is the eutectic, right? Here another one, lead and tin, right? It changes. So this is the change, right? So this is the eutectic solidifying temperature, right? So I have added some of assignment, that means classroom assignment. So after this lecture, you can do that one and send it to me. Then binary we call peritectic, right? So peritectic means, so you have to memorize these wordings, right? What is called isomorphous, then what is eutectic, right? So what we here eutectic, and now what is called peritectic, because seeing those kind of phase diagrams, you have to identify if this system is going to be peritectic or eutectic or another isomorphous or likewise. It is why these wordings are important. So peritectic reaction means liquid phase react with the solid phase to form a new different solid phase, right? That means liquid phase, so the formation of liquid, after both are solidifying, it composes a liquid. So that liquid phase will react with the solid. It means you have the solid plus liquid phase in between a liquid phase and solid phase. Right here, uh, this one you can easily identify. In between this, right? This is so after this line you have liquid. Before this line you have solid. So in between these two you have liquid plus solid. So in between this area they are forming another solid state. Right? It is called peritectic. That means liquid plus alpha they have developed called beta, not liquid and alpha. Right? So here you can see from this point to this point only you have L plus, that means liquid plus the solid alpha. If you say alpha, then liquid plus solid alpha. But in the peritectic one, they said liquid plus alpha is changed into a solid called beta. Right? So peritectic reaction occurs when a slowly cooled alone. Right? As example, ferrous and nickel. This is also a binary system, but if they going to have kind of a cooling process, right? If you add 4.3% of weight nickel, right, then at the point of 1570 degrees Celsius, they are forming another solid called beta, right? So normally we can predict, so they are doing that kind of binary system, but in between that, at this kind of special cases, right, that is one of a effect of having those different structures, right? You have CC, BCC and all of this stuff. So at the temperature that is also specific, like 1517, if you have 4.3 weight percentage of ferrous at the point, so they said they are developing one of a different solid phase, right? This is like this liquid, that means 5.4 weight of nickel plus then delta 4 weight nickel, right? If they cool, they form called gamma, right? In that phase you have 4.3 weight percent of nickel, right? That is a kind of a peritectic system. Here you can see, right, in this case, this point, after this point they are forming another one, right? Not this point, these two, they have another form is there, right? Here you have this is kind of a again complex system, but you can identify a line between here, right? You have liquid phase. So if you go through this line, if you go through this alloy L1 line, right? So it's right, then you can see here liquid, right? In between that you have alpha plus liquid, but here that is change, right? Because here you can see there is another melting point, right? A melting point is there, but you know that a binary system, we can't see any melting point in between these two, but here you have a in between melting point. So that means you should have a particular single phase, single solid to have a liquid like this, melting point like this, melting temperature like this. So that means in that case you have only one solid phase. So after liquid, then liquid plus alpha, liquid plus solid. So in between you have a melting point line, means there is a single solid is formed, right? So that composition we call peritectic alloy. So in that peritectic alloy you have only single phase solid there. So after that again here also you have components alpha plus beta, both are solids. So in that case you would not have any kind of lines here to show this type of melting point. So that means that is a composition. But in this line you can see there is a kind of a melting temperature, right? So here as examples, at 42.4 percentage silver at 1400 degree Celsius, right? You have a liquid composition 55 silver and alpha phase you have 7 silver, right? So that is also one of a peritectic system, right? This is platinum silver alloy, right? So those are the things that you need to refer in your future cases to identify. Here this is, can you see this point, this point? Peritectic point. Peritectic point, the point on a phase diagram where reaction takes place between previously precipitated phase and the liquid produce a new solid phase. When this point is reached, the temperature must remain constant until the reaction has run to completion. So likewise here, it seems after this we have beta here, not alpha, right? So solid alpha is formed in this case. Those are some of the reactions. So a peritectic reaction where solid phase and liquid phase will together form a second solid phase at a particular temperature and combustion. So you have a liquid and alpha region. In some temperature only beta exists, not alpha or liquid, right? Within these two. So in that case you have you can identify that is called peritectic, right? In this one also, so after this point you can see there is no alpha, right? After this point here also you have, and again alpha plus beta, but after that this is the liquid phase. You can see point here to here change, no, from here to here change. This is TA and this is TB. So total is changed from here to here. You know, that is the general rule, right? This is the total A, and you have the melting temperature A. This is the total B, that is the melting temperature B. From the system, that is changed from here to here only, in between that. But in between that, you can see there is a change of melting temperature as well. So that position, you can see after L and alpha, right? So there is no any phase of alpha. They form only beta. After that temperature you are forming only beta, right? So it is the peritectic. Then you have another one called monotectic. So monotectic describes the isothermal reversible change of a liquid phase to form a second liquid phase plus a solid phase during cooling. So here, so please identify second liquid phase, right? This is a monotectic system. You can see only this one is a L1, but after some time you are facing another L1 plus L2, not this one. So it forms. So here normally it goes like this, but it change up to some, right? This is L1 cooling. This is the cooling curve, phase curve. This is a liquid curve. L1 change alpha plus alpha L2, not L1, right? So two liquids are immiscible. Example, copper lead. System at 9550 and 36% lead. So if you have 36 point lead and your temperature is 9550, right, you can see another liquid phase is forming. Right here you can see a table. So these are total systems that you can identify under binary system. Eutectic, total liquid. If you cool, it forms alpha plus beta. Right, phase diagram characteristic from alpha to beta only. Then again we identify what is peritectic. Peritectic means alpha plus liquid is form another solid. Alpha is a solid and liquid. Then there is a system called alpha plus liquid. So after cooling it forms another phase, only solid phase is beta. You can see in between A and alpha and liquid you have a beta phase. Then now we discuss what is monotectic means. Monotectic means a liquid phase is changed to another liquid phase plus solid after cooling, right? So that is the monotectic. So another two is there, Eutectoid and Peritectoid. Tictoid, right? Please notify that one. Tick means you have liquid at the first stage, it goes to another stage. That means it may be solid or solid plus liquid, right? Tick. If you have a tick phase, you are starting one is liquid. Here, peritectic, you have starting liquid. Monotectic, you are starting liquid. Right? It goes to another solid plus liquid or something, right? But eutectoid means you are starting from toid, starting from solids, right? So in between those two A and B, you have only phase of solid transferred to two different phases of solid. It is called eutectoid. Peritectoid means different phases combine and phase and form another third solid phase. It is peritectoid, right? So this figure is very important for you, right? So after getting some phase diagram example, we can identify this one. That is the most important part of your phase diagrams and this learning outcomes. Then the eutectoid I have described. The Eutectic reaction describes the phase transfer from one solid to two different solids, right? After that temperature, with the given composition, it has changed into different two solids, right? As like this. This is TA and TB, right? You can see the difference. Here, normally it goes to this, but it different from this kind of angle. So alpha, right, it changed to alpha plus gamma. Only alpha is changed after this point, alpha plus gamma. So here this is the gamma solid phase, this is the alpha phase. But after alpha it changes to different solids. Like this is also eutectoid steel. Then peritectoid describe the isothermal reversible reaction, multiple solid phases to form new system of fewer solid phases during cooling. Right? That means you have two different solids, solid 1 and solid 2. So after cooling, you have new solid 3. Right? So this term is very important, cooling, during cooling. But after forming new solid 3, you can see heating, you get solid 1 and solid 2. You can see this is a called eutectoid. Because eutectoid means one solid into different solid. Here also same after heating. But these two are different because it is going from the cooling phases. right? So in this point also you have this is alpha and this is gamma phase. So in between alpha and gamma you have alpha plus gamma, right? This is beta, right? But if you have like this one, right? So there is no combination, that is gamma plus beta. Those are solids, right? But liquid is something higher than that, right? So starting from solid 2, it becomes that means a different solid, as like here. If we say this is the alpha plus gamma, so after this point, right? If you explain, consider this EP, this point, right? I think you can understand, right? If you compare this EP, if I want to show it like this in this point, right? Here you have alpha plus gamma. This is the phase, right? This one also. Here also you have alpha plus gamma. But after EP point, if you cool down this one, because this region, you can easily identify this region. That means this one, right? This region. Up to this point, after this point also, you have alpha plus gamma. So if you cool down this is the EP, we call this peritectoid point. You have alpha plus gamma solid, right? So if you cool it down, right? If you cool it down from here to here, you can see the difference, because you have alpha plus gamma here, right? If you just cool it, it converts to beta, right? So after this point also you have the composition of alpha plus gamma, but sudden cooling, that alpha plus gamma convert to beta, right? So actually we just can't signify that one, because we know that if you have alpha plus gamma, if you just cool it at the liquid phase also you have this alpha plus gamma, but now it's same. If you cool it, it changes to beta, not alpha, not gamma. There is no constant of alpha or gamma there. So that point, this point also, we call it peritectoid. Right? So I think now you can identify, you can grab something about what is behind our phase systems, phase diagrams, right? So this is a phase diagram. Here you can see this is the gamma phase, this is the alpha phase, this is the beta phase. So there are different arrangement. That means the composition change from A to B, right? Only two phases. There are tertiary diagrams also. Tertiary means we have third element also. But here you need to understand only about two phases, two diagrams, two elements, binary. Right, from A to B, change. This is the POA and this is POB. From A to B change, you can see how many changes will occur. So that means you have different phases, different solid phases, right? Form. Alpha is a different phase, gamma is a different phase, and beta also different phase. So using this A and B compositions, that means you can see to form alpha, right? This is the boundary of forming alpha, right? This is the boundary of forming alpha. So in this boundary, if you just draw a line from vertically, right, as example, if you just draw a line from here, in this point, you can identify what amount of alpha there are and what amount of A and what amount of B, right? If you just cool it to a temperature like here, you can see you have only alpha phase, alpha solid. It is not same to A, it's not same to B. In between A and B, you have formed alpha solid. Also in between, you have formed beta solid. And you have a composition around these, that means the temperature also there. Below this temperature, right, the composition may change from A and B. You formed alpha plus beta solid. That is how we are describing this phase diagram. Here, this is a total systems are there. You can see the total system and you can identify total systems here. Try to enlarge this one to identify. This is the total summary of what we have discussed. Right, so I think all of you can see. So first one, we identify what is eutectic. Right, I think you know what is eutectic means. This is the x point and this is the y point. So in between x and y, this point is below than x and y. That is why it is called eutectic. Right, so tech means it start from liquid and now you cool down. Start from liquid, cool down. Then another tectic is peritectic here. It start from liquid and goes to cool down, start from liquid. Again, monotectic, start from liquid, then goes to start from liquid, then go cool. So in these three systems, eutectic means, right, you have different melting temperature below these two, right? So if you just cool it, it change to different phases, gamma plus beta, right? So after cooling L2, you are forming two different solids, gamma plus beta. It is called eutectic. Then monotectic here, you can see L1, it changes to L2 plus gamma, right? L1 is the liquid, starting liquid. So after monotectic point, monotectic temperature, it changes to L2 plus gamma, right? That is how it changed. Then it says monotectic. In the peritectic point, you have alpha plus delta. It changes to third different phase called gamma solid. Liquid plus delta solid changes to different solid called gamma. It is called peritectic. So after this point, if you have a phase diagram like this, then you can identify these points in the phase diagram. That is the main objective you need to get from here. So this is the tick points. Tick means starting from liquid to cold. Then toid points here, it start from solids, then just cool down. This is Eutectoid and Peritectoid like this, right? In the Eutectoid, starting from gamma solid, then you cool it, it just find another two different ones here. Right? So starting from gamma solid, you cool and you are forming alpha plus beta, different two solids. Right? It is called eutectoid. Then peritectoid means this is the alpha plus beta solids, two solids. You cool it, now it form mu. That means another different solid. That means only one solid phase. Here two solid phase, but now it different from that also, but it form only one solid phase, right? This diagram means, right? So up to this point, if you have any questions,